Hello everyone. Let's just wait for everyone else to join in. Hi Rohi, I hope you can hear me.
Yes, hello.
Okay, I see Sarangs has joined in as well. So let me share my notebook and then we can start. Hope you can see it. So just a quick recap of what we did yesterday. And I had asked a question, so you can paste your answers in the chat and we can discuss. So we looked into some specific visualizations. We looked into box plots. We moved over to violin plots. And then I had asked a question as to what this belly of the violins mean. So we would like to know what they mean basis what you may have already found out. If you have not found time to research that, it's all fine. You can write that on the chat as well, no problem. But if anyone amongst you has found out what this exactly means, it will be interesting to know. Right. And then we looked into the joint plot. So we started doing the discussion on the joint plot, and we came to know that uh, we can try to use the analogy of coming down from the hill of a mountain, and there can be numerous number of ways in which we can come down from the hill of the mountain to the tip or from to the bottom of the mountain. And basis what route we are going to apply is what is going to define our strategy. So that's what we will be discussing uh, from here. Okay. So okay. Okay. I have got one answer from Sarangs. I'll wait for more answers. Maybe we can discuss at the end of this meeting. Yeah. So let's try to continue with what we are trying to do, and then we'll see how we can go. So what we were doing yesterday is that we have a mountain like this, and I am standing here. So this is me, and I would like to come down. So this is, let's say there is some price over here, and I would like to come down to here. So there is, here I have 180-degree circle. On the other side, I have a 180-degree circle, which means on the all of the sides, I have various different ways in which I can come down. Okay. Please do remember, I can come down from the other side of the hill as well, and then I can take a small walk from the back side into the front side to get the gift as well. So I can come from here, I can come from there, right? So it is not a mandate that the gift is over here, and that's why from this side. So let's say this side is side one, and the other side of the mountain is side two. So I have to come down from the mountain using side one only. That's not the case. I can come down from side two as well. Okay, I just have to reach the price. Okay, so that's the idea here. Okay, that's what I'm trying to do. So I can take any route. Okay, now the names that we started giving to things are like this gift that I have over here. This is known as the local minima. Okay, this is where I would like to reach, and this entire problem, this entire exercise of a person, in this case that's me, coming down from the top of a hill uh, towards the bottom of the hill where I have a gift, is known as an optimization problem, otherwise also known as a minimization problem. Why? Because every route I take, let's say I take a route like this, okay, or I take a route like this, okay, or I take a route like this. So this time I'm coming from S2 maybe, and then from S2 I come over here, and then I come over here. So irrespective of what route I take, so let's say this is R1, this is R2, and this is R3. Irrespective of what route I take, my objective is met, right? My objective is clearly met. Okay, so you can say that there is practically no difference between the R1, R2, and R3, because ultimately the person who is at the top of the mountain, in this case, that's me, I'm actually reaching the bottom of the mountain to the gift. But then imagine how much effort it takes for me to take the route 1. Let's say that is effort 1, okay, E1. And then for route 2, I have to spend effort 2. And for route 3, maybe I have to spend effort 3, okay, E3. If E2 is the lowest among E1 and E3, then why not I choose E2, right? If it takes more energy and more time for me to reach the bottom of the mountain using E1 and E3, then they are not efficient ways to reach the bottom of the mountain. I'll get tired, right? I'll have aches in my legs as well. So I don't want to get so much tired. I just want to reach my gift, which means if I do a comparative study of the effort E1, E2, and E3, then I clearly see that E2 is the best way to come down. But then there is a problem. There is a big, big problem here. There can be n number of ways in which I can come down. So R, okay, basically can range from R1 until Rn. N can actually be infinitesimal because there are two sides of the mountain. There are infinite ways in which I can come down. And then accordingly, so effort wise, there can be E to En, okay, efforts, each of the efforts linked to each of the routes that I've taken. So there are infinitesimal possibilities in which I can come down from here. So this is my start and STA, and this is my stop, so STO, right? So from start to stop, I have infinitesimal ways in which I can reach. So why this problem is called a minimization or an optimization problem is to find that one route, let's say R of M with an effort E of M, okay, which is the minimum amongst all the efforts. So that is the reason why I'm trying to optimize my efforts by finding the minimum, okay, or finding the route, or this optimized route is what I'm going to find by minimizing my efforts, or where my optimized route has the minimum effort, right? So that is why this is a minimization problem. So let's say I'm standing here and I can come from here to here. I'm standing here, I can come from here to here, right? Or I move over to here and I come from here to here. So these are all my E1s and E2s and E3s and so on, right? So I hope you have got the concept now. So what is that one EM? Okay, what is that one effort or that belongs to one root R of M, where EM is actually lowest as compared to all the other efforts which you have. If I have that figured out by some kind of a mathematical operation, when we do machine learning, we are going to see one of the ways in which we can do that. I am going to quickly tell you one of the ways, right? So if we can find that one way, then that is going to make my life easier. And my objective is to reach over here. Okay, as of now, you may not understand why I'm trying to reach over there, but that's the objective. Okay, just keep this in mind that that is one of my objectives when I'm trying to do machine learning, or when I'm going to do any kind of, let's say, modeling. That's going to be one of my objectives which I want to fulfill. I would like to efficiently reach the bottom of the mountain towards my gift. And one of the, let's say, algorithms or one of the methodologies by means of which I reach that local minima is known as gradient descent. So gradient is just these areas, or you can say these circles which you see over here, like this hyperbolic or elliptical structures that you see over here. These are one of the gradients. So as you can see, if you come closer to my gift, the hue, the gradient is actually becoming dark, right? So that's why they are called the gradients. And I'm trying to do a descent. I'm here at the top and I'm trying to descend down to the bottom. So that's why this algorithm is very cleverly named as gradient descent. So this is a very famous and very important optimization problem or optimization algorithm by means of which when we actually do modeling, we are going to reach the local minima, or we are going to reach the bottom of the tree. Okay, we are going to reach the bottom of the mountain. Okay, and we need to reach the bottom of the mountain because later we will come to know that the amount of time it takes. Okay, the amount of time. So time, let's say Tm. Okay, so if there is a route Rm that takes effort Em, let's say the time it takes for me to come down from the top of the mountain to the bottom is given by Tm. This Tm is going to decide how much efficient, okay, it is going to decide how much efficient, okay, my algorithm is when I'm trying to model the data, irrespective of the size of the data. Are you getting my point? Here in this case, you have a toy data set. You have only 150 rows. In real life, you will have a data set 150 MB, 150 GB maybe. Not only 150 rows, there will be 150 GBs of data. Then how do you train a model, or how do you fit a model? How do you apply a model on the data size that is this much huge? And then again, that data is not going to have only one variable, which is going to have a plot like this or a structure like this. Here I'm trying to compare only two. Why I have only 4 features? Now imagine you have a 150 GB data set, okay, 150 GB data set where you have 300 columns, okay. Try and imagine how much difficult it will be to figure out the optimal time for each and every of these contours. Okay, these each and every blocks, these blocks are also known as contours. CONTOUR, right? Each and every block is known as the contour, right? This contour is simply representing the different areas based on the petal length and the petal width, or when we compare petal length and petal width, this is the setosaflar. If I remember this correctly, this code that we have written over here is for the iris data. Okay, this is for the entire data, sorry. So this is not for one of the data sets, it's for all. Okay, so for entire data set itself, irrespective of the species of the flower, these are the two contours which are created by the combination, or when I try to compare petal width and petal length, these are the two contours which are created. Now imagine how many contours can be created with a dummy or with a simple data set like iris, right? Then compare that to my example where you have 150 GB of data and you have 300 columns. There are ways, we are going to look into ways to reduce these 300 columns down to factors, down to meaningful number of factors, but that will come at later stage. As of now, upfront, you will be facing a lot of problems, right? That's where this is an efficiency kind of an algorithm. It's similar to, as I told you in the last session as well, similar to my ON, or the complexity of any programming algorithm which I use, right? So that's the first objective, to reduce the time, to reduce the number of time I need. Okay, the second objective of drawing this contour plot at the first place, let's go back to the basics. First of all, we wrote 3 lines of code or 2 lines of code to draw the plot, right? Then we came to all this mountaineering thing and so on. So why did at the first place we draw the plot? The first place we draw the plot because we wanted to know what kind of contours exist. Okay, now imagine, try to just understand what kind of a comparative study we can do. So let's say this is my actual output, right? So I'll call this A. Okay, this is my actual output. So let's say I'm going to draw some other output, which is my imaginary output. Okay, so imaginary contour plot, let's have some other situation, some other data set, some other scenario is something like this. Okay, some other scenario that I have drawn, I have seen a contour plot which is something like this. Okay, not a very good diagram, but I think you have got the point. Okay, the point that I'm trying to make over here is, if you see over here, I have a bifurcation. I have 2 contour plots. A combination of entire iris data depending on the comparison of petal width and petal length, irrespective of in which axis they might be, that is irrelevant. In this case, let's say I have any column x1 and x2. I'm trying to compare those two features in any data set D1, and I come to an imaginary contour plot IC, which is a single cell. Okay, it's a single celled organism kind of a thing. Here I have 2 cells. Here I have only 1 cell. Now you have to tell me which one looks to be more efficient. Clearly, only by looking at the diagram, this you can see is going to be more efficient. E of I, let's say this is, and this is, let's say, E of A. Okay, the overall or average efficiency of the actual contour is, let's say, E of A, and that of the imaginary contour is E of I, and I can clearly say that it is EI is actually better than EA. Maybe Saransh, you can unmute yourself and ask the question.
Bowman, just a question. So
Yes.
these two dark spots, right? So these two dark what does it represent? I mean,
Your gift.
does it represent the maximum data points which are lying at
No, no.
a
It
particular
simply
point?
represents the bottom of the mountain. It simply represents where you need to reach. That's all.
Okay,
Right? It
okay.
simply represents what where you want to reach. And why do you want to reach over there? Try to compare this with this. Because this is a bimodal data, these black points are actually referring to the mode. The one which is on these two axes, these are the distribution diagrams. Right? You see there is a mode 1 and there is a mode 2. And these two modes
Yeah.
M1 and M2 belong to petal length. So these black
Mm-hmm.
points are actually intersections of, let's say, this is M3 and this is M4. So this point is an intersection of mode 1 and mode 4. Well, mode 1 belongs to petal length, mode 4 belongs to petal width. So it is a concentration point where many of the points are actually concentrated. So in one way you are right, but then we don't consider it that way. Right? We are not going to consider that in that way. Then it is going to bias us. Then it is going to lead us into a different way altogether. Right? If you are going to call that the place where most of the data points lie, then it will seem that as if I'm trying to only be interested or inclined towards the mode and not the rest of the data. That's not going to be the case, right? So I'm not only interested in the mode of the data where I have peak in the mountains in this curve, right? So I'm not only interested in these points, I'm interested in all the points. And that is the reason why, considering all of the points, I'm trying to come down from the top of the mountain to the bottom of the mountain, so that I can find a route. I can find the best route to reach from X until Y.
I think now the mountain thing stands clear.
Clear,
The
right?
way you're
Okay.
describing. Yep, yep.
Okay. So that's one way. So that's one of the things I wanted to discuss. Please don't worry right now. I know there can be questions. There will obviously be questions, but it will get clear more and more as we practice and more as we are going to deep dive into modeling part. Okay. But before we go over there, last class I was talking about something and I did not share that data. That is a mistake from my side. And I will just share you certain notes. So let me just write this in the chat window, and then I'm also going to share this on our LMS. So I would like both of you quickly, if you can do it, maybe post this call, that will be great. Go to a website called kaggle.com. Okay, and search for a URL. Let me just paste the URL. I've copied it into a notepad. You won't be able to see the notepad, but let me just paste it over here. So there is a data set that I've just pinged you. This is called Haberman Cancer Survival Data Set. Okay, this does not reveal anything, or it does not point you to anything. So don't try to infer anything out of this. That is not the exercise that I would request you to do. You can, okay, you can. Okay, you can do. I mean, I'm not stopping you to infer any outcome or any prediction or any inference from this. Okay, you can do that. But as of this point, I would like you to go to Kaggle. If you don't have an account, don't worry. Try to log in with your Google login. Okay, so let's say you open this website from Chrome, and there is a sign in option. So you go to sign in, directly use your Google credentials. There is already a linking there. So try to use your Google credentials to go inside. Okay, complete few basic things in your profile. Come back to this URL, and here you have the data set. Okay, inside Kaggle itself, you can create a notebook and you can start to play around with the data. Okay, so when you open the Kaggle, I'll just quickly show you, and this is really a very important thing, right? I would request every one of you to do this, both of you to do this. Let me just copy my link once more and come over here, and let me just search for this. I'm not able to find this, but okay, there are people who have already done some EDA, right? I would strongly recommend you don't look at them at the first place. Try to do it yourself first, and then you can look at them. Okay, don't look at the solutions. So it's not like an exam, but I would request you not to look at the solutions first. Okay, so this is the website. I have not logged in here yet, so you can see the sign in option here for me. So you can sign in, and then you should be able to see, let's say, the data. So there is a data which is haberman.csv, and you can see a description here as well. You can clearly see what this is containing. This data set contains cases from a study which was conducted between 1958 and 1970 in the University of Chicago's Billing Hospital on the survival of patients who have undergone a surgery for breast cancer. Okay, so there are people who underwent a surgery for breast cancer, and this data set contains some information about them. We don't know what that information is. It's clearly their age, the year in which they were operated, axial nodes. We will have to find out what this is. Okay, I'll leave this up to you. Axial nodes is actually a medical terminology. Okay, axial nodes is just a characteristic. Okay, you can find this from here, right? You can find this from here. Number of positive axillary nodes detected. Okay, auxiliary nodes is how many axillary nodes were there in the breast of that particular patient. How many cancer points were there, right? You can also study more about this, but this is the basic idea. You have got four columns, you can say, and then you can try and analyze these four columns, right? So you can try to find out, or you can try to repeat the exercise. I'm going to upload my notebook into the LMS as well. Try to go through each and everything that we have practiced. Okay, try to find out the scatter plots, the descriptions, the information, and so on. Okay, try to publish that into Kaggle. Okay, you must publish that either into GitHub or into Kaggle, irrespective of how good or how bad your analysis was. Okay, if you want me to do some analysis as well, I will also do in my spare time, and I'll share my let's say GitHub link or my Kaggle profile with you, so that you can look at that notebook as well. Or maybe I will download this data and do it locally. You can do that as well, by the way. You can download it and you can do it locally. But I would strongly recommend you can make use of a certain thing which is really, really very good. You can sign in with Google. I'm not sure whether it's going to work for me right now, because I am into my office laptops, hence I'm not sure it is going to work for me, but let's give it a try if it works. So you can log in with your, let's say, Gmail ID, and using this Gmail ID, you can sign in. And once you are signed in, you should be able to look at the data. And most importantly, what you can do is that you can click on this new notebook option. You see over here, you can click on this new notebook option, and then a new notebook comes up. Okay, this notebook is exactly similar to what our notebook is. You can select what kind of programming language you want to use. In our case, it will be Python, and I would like to have an interface similar to notebook. And if I click create, then I can see that the new kernel is created. Kernel is nothing but a notebook. Okay, it is just a Python code which you can reuse, share, and do a lot of things with it. If you want to know how Kaggle works, you can go ahead. I'll also give you a detailed description about what Kaggle is later on, because when we are going to do projects, we will primarily use Kaggle, and we will also use GitHub to create our profiles. Okay, now this will take some time for you to load, but there is a huge advantage. Huge. It is giving you GPU, CPU, hard disk, and RAM for free. Okay, it is there for free. You see, these are the metrics: disk space, CPU, RAM. These kind of things are already given for you for free. Some of the libraries are already imported for you for free. Okay, this is a code block. If you execute this, you get an output. Okay, this is how you can write your code. So let's say I'll give this some kind of a name. So this is what Haberman survival, or I will say Haberman cancer survival. Okay, I'll give it a name for version 1. Right, so this is the name that I have given, and now I can see my input is here, and in the first block of code, it is saying it has already imported NumPy, already imported pandas, and it is showing me where the data file is. So simply I can write over here, let's say I'm going to call this read CSV, and here I'm going to enter this. Okay, and now see, I am able to do all my analysis online. And the moment you think you have reached a certain point in time, do a save version. Okay, this is version 1, and you can do a quick save, and it's going to save that for you in your profile. So why I'm saying this is important for you is this: I'll take this link from here. If I open this, Now in my Kaggle profile, I can see that I have created a notebook. Okay, I can go to notebooks and I can clearly see I have a notebook called Haberman Cancer Survival V1. Later on, if my notebook is really very good, I'm going to publish this. I'm going to publish this to inside Kaggle. There are a lot of people playing around into Kaggle. They are going to look at my work. They are going to appreciate it. There are recruiters as well. Okay, there are people who are intentionally logging onto Kaggle only to look for good talent when it comes to data analysis. This is really important. Okay, this is not for only for the fact that I'm going to run a few Python commands that I could have done using my laptop also. I shouldn't have been going into Kaggle, right? We have already installed all the softwares, right? So we could have done this in our laptop. The reason why we are going to Kaggle is so as to get the visibility, so that we can create a community or we can be part of a community. That's what is going to be the most, because here people will not only be able to look at your a kernel or at your notebook, they will also be able to enhance it. They can clone it and they can suggest you, see, I would have done this analysis in so and so way, and you would have got a lot more results. Okay, this is really important. Please take this very seriously, and you must have this in place. Once you have this in place, you do some kind of an analysis, let's say basic statistics of the data, and then you are going to say, let's say cancer dot describe, right? This is the command which we use to get the 7-point statistics. So you get that output over here. Try to find out as much information as possible, create markdowns and write your findings. Okay, don't only write code, write your findings. Give some good heading, give some good notes, give the background. You may even want to copy paste the description which you have found from the internet or from the same site. Then you put it over here, write down each and every finding that you have as if you're explaining that to a cousin who is 6 years old. Okay, so be as simple in your language as possible. Try to write it down over here. Okay, maybe I'll do some analysis as well myself. Okay, and then I'm going to send you my version as well. Okay, so that you can uh, look into the version, but please do practice from your side first, and then we are going to look into rest. Right, this is really very, very crucial. Right, as I said, there are people who are actually doing paid competitions onto Kaggle just to find out people who are really good into machine learning, into data science, into data analysis, and they don't look at your code. Okay, trust me, they are least bothered about your code. They are least bothered about how efficient your code is until a certain point in time. The first thing they will notice is your approach. If you have done exemplary data analysis, you get the attention. Then they will look at what kind of libraries you have used, or how good a coder you are, or what kind of let's say mechanism you have used, whether you have used gradient descent, for example, properly or not, and so on. So technicality will be taken care of at a later stage. At the first place, they'll only look at the approach that you have followed. That's really very important. Okay, I would strongly recommend that you please go ahead, create an account if you don't have one. You can give a good photograph as well. I have not yet given this. This is just my new account. This is just my new Gmail ID. I have another one. So from there, I used to practice earlier into Kaggle, but that got lost. So I'm going to make this as my a professional profile itself. You can also take that into account, and then you can do as much analysis. I would like to suggest as much as you can. Okay, spend a lot of time, try to do as much analysis as you can. Right. That's it. As of now, we have looked into a lot of, let's say, points, a lot of areas related to the analysis that we can do. There are many other things that we can do, but as of now, we are simply going to conclude that we have looked into a lot of areas where we believe this is really going to help. Okay. So that's something that we have covered until now. If anyone has any questions until this point in time, before we move into actual inferences, please let me know. Is there any question from anyone?
From my
Okay. 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 Give me 1 minute. I opened the link, but it is not working. I don't know why. I'm not able to find that link. Give me 1 minute. I was searching for a data set actually because I need to carry on with the rest. Okay, let me see what we are doing. I got one. Okay. Okay. Let's start with this one. Let me load the data. You wouldn't be able to see my screen right now. I'm doing it in a different window. I'm trying to download some data if I can. If not, we're going to use some, let's say, dummy data. And what we are going to do is maybe I can call this part. Okay. Now let's try to move over to inferential statistics. Okay, we have seen certain things into inferential statistics earlier. We are going to look into some of them at least over here. Some of the tests that we have done earlier, right? We have done what? We were doing hypothesis testing using Z value, right? We briefly look into T values, but before going into T tests, we also looked into P value, right? We found out why P value is actually better than the Z value. I hope you do remember, because in Z there is always a confusion of this on which side it is going to fall and what will be the critical region, what will be the value which is going to be greater than what and so on. But with P value it's really easy because I have a confidence interval, right? And then basis the confidence interval, I can try and find out uh, where the p-value should be lying so that I can get the actual, let's say, probability. Okay, so there are, let's say, oh shit, I think there are actually libraries by means of which we can do that. Somehow this thing is not opening. I don't know why. Hi all. Can you hear me?
Hello. Yes. Yes.
Yeah.
Yes,
Okay.
Tom.
Oh, sorry, there was some kind of a network problem. I believe that is the reason why I was not able to download my data set. So let me just quickly try once more. Let's see if that works now. Let's see if that doesn't work, we'll have to continue in the next class, but let me just quickly show you what I wanted to do. So I would like to do this in two ways. So first of all, there are two approaches that we are going to follow. Let's write it down over here. So sorry, approach one. Okay, I think I'm back now and you can see my screen. So approach one will be create some kind of a dummy data and apply the hypothesis testing. This is going to be our backbone. Okay, this is going to give us the necessary skills, I would say, to understand what is happening here. The moment we understand what is happening here, we can use any data set and then we can do any kind of, let's say, hypothesis testing, right? So first of all, we will take some kind of a dummy data set and then we are going to do the hypothesis testing, and then let's see how we can do the rest of the tests. Okay, and then the other way of doing the test, approach two is going to be use existing data like iris and find the hypothesis. Okay, I think it will be interesting to start with point number two and then we can start with point number one, or maybe we can start with point number one first. Okay, and then we can go ahead with the rest. Okay, so now how to do point number one. So or maybe we can start with two also, and that is not going to be a problem. Give me 1 minute. Okay, so have I imported SciPy? SciPy as SPS, I've imported SciPy. Okay, now what we need to do hypothesis testing, to perform hypothesis testing, we need data, question, and confidence interval. All right. When we have a confidence interval, CI, the market standard is 95%, right? So that is the market standard that we have already discussed about. So if that is the, hello, I hope I'm there, right? Yeah, I'm there. Okay. Is my screen not visible to you? No, right?
Yes,
It's
it's
visible.
now visible.
Okay, okay, okay. So what I was saying, we can use two approaches. One is to create the dummy data. That's from where we are going to start. And then the next approach will be to use the existing data. Now, when we are going to do hypothesis testing, we need three things. Obviously, we need the data, we need a question, then we need the confidence interval. Confidence interval, nobody is going to tell you in the market. Okay, in the industry, nobody is going to tell you. You have to take the market standard, and that is 95%. If that is 95%, if you remember from the basics of statistics that we have done, okay, there was a parameter which used to define the criticality, right? That parameter was given by alpha, and that parameter is 1 minus the confidence interval, right? And that in this case, so confidence interval is a probability. I am 95% sure, or I'm 95% confident. So what becomes of CI? CI in probabilistic terms becomes 0.95. Hence, this value becomes 0.05. Okay, so first of all, we need to define a variable which is 0.05. So I'm going to take the alpha value as equal to 0.05. Okay, this is my uh, confidence level of what I'm going to do. Right now, what I am going to especially do, give me 1 minute. Yeah, okay, yeah. So uh, now let's say my question is, how comparable or effective is the sepal length of my flower, iris flowers, as compared to petal length? Okay, in other words, now this is not a data driven kind of question. We have to convert this into a data driven question first of all. Okay, so let's try to find out how we can really convert that. Okay, so let's say R or better question, are the distributions comparable with each other? Okay, so this is so one more way to ask the same question: distributions of sepal length and the petal length for iris. Okay, so what we would like to do, I don't think we have time right now, so we are going to continue in the next week. So what we are going to do is that we are going to solve this problem using the tests that we have done earlier. So we have seen the formulas, we have not seen how we can do these tests, right? So when we are going to do these tests, what essentially we are going to do is that we are going to use this SP SciPy, and here there is a module called stats. Okay, stats is a module, and inside that module I have a lot of functions, and I have these functions inside stats which you can go through in the documentation as well, which lets you do the tests. Okay, so there are a lot of tests that you can do. Example given, binomial test. Okay, there's chi-square test. Okay, then there is a chi-square test is something we have not really looked into. Okay, so there are other tests as well that you can do. Let us find if there is anything that matches what we have already learned earlier. Okay, so let's say we have a test which is known as the t-test. Okay, so we have t-test here. Okay, so we have t-test for one sample, and we have t-test for independence. Okay, so these are the tests that we can use, and we can try to find out if there is any relationship between one of the distributions as compared to the other distributions. Then we are also going to do some tests which is going to tell us what is going to be the value relevant to p. So what is the p value? We have to find out what is the p value, right? If that p value is less than alpha, then the probability of the null hypothesis is very less, and hence the alternate hypothesis is going to be correct. Okay, so in this case, final question we can say, okay, sepal null hypothesis, okay, is equal to, no, I think the session is going to end. Okay, no problem. I think we can end here. And then we can continue in the next. I would strongly recommend once more before closing the class, before we meet on Monday, please spend some time on the weekend creating your Kaggle profile and the link that I have given you. I'll also mail you, don't worry. Please look into the Kaggle profile thing. It's really important. Okay. Let's continue on Monday. We'll start from formulating the hypothesis or the questions, and then we'll look into the analysis. Okay. Thanks all. Have a good weekend.